composite functions. So basically a composite function is where we combine two functions together. So for instance, here's a set of x values, and if we plug it into the function 2x plus 1, well then the 1 would become 3, the 2 would become 5, the 3 would become 7, the 4 would become 9, and the 5 would become 11. Any x is going to 2x plus 1. If we were now to plug that into a new function, 3x squared, well now the 3 goes to 27, the 5 goes to 75, 7 goes to 147, 9 goes to 243, 11 goes to 363, but basically the 2x plus 1 is now going to 12x squared plus 12x plus 4. So we could combine those two functions into one, 12x squared plus 12x plus 4, and when we sub 1, it would go straight to 27. When we sub in 2, it would go straight to 75, and so on. So it combines the two functions together. So the way we write it is like that. Okay, so what we're saying is we're substituting function x into gx. And so it becomes 12x squared plus 12x plus 4. Now, if I was to substitute it the other way round, usually you'll get different functions. You've got some special functions that you get the same one, but they're rarer. But usually you'll get a different one. If we were to sub gx into function x, then our composite function would become 6x squared plus 1. So we'd get a different function. So the question now is, well, how do we find the domain and the range of these composite functions? Because we have to be very careful. So basically, you've got to satisfy these conditions. So first of all, if I'm going to substitute gx into function x, well, x first of all must be in the domain of gx, because if I can't substitute it into gx, then I can't substitute it into the composite function. But additionally, those answers that we got out must be in the domain of function x, because if my answer can't be substituted into function x, then also it can't be part of this composite function. And then when we're looking for the range, so a value of function gx, so the answers that come out, it'll be in the range only if its x value was in its domain. Sounds a bit strange. Well, let's have a look at the example to see what we mean. So function x is going to be 2x on 4 minus x. G of x is going to be 1 on x squared. And we want to find the domain and range of the composite function. Okay, well gx, its domain, if I was just to find the domain of gx, we know it'll be all real numbers, but excluding 0. So we know 0 can't sub into that. So our range would actually be greater than, real numbers that are greater than 0. So function x, the domain, all real x, but this time x can't equal 4. And the range, we will never get the answer -2 for this particular one. We'll never get the answer -2. So x must be in the domain of gx. That was our first condition. So if we look at gx, we said x can't equal 0. But we also said gx must be in the domain of function x. So gx can't equal 4. So go back to what we said about gx. Okay, we're saying gx must be in the domain of function x. But function x, the domain was, it can't equal 4. So therefore, even though gx might be able to equal 4, I can't substitute that value in. So back over here, we get, so gx we know can't equal 4. So 1 on x squared can't equal 4. That means we can't substitute in plus or minus a half into this composite function. So our domain for the composite function, we know we can't have 0, but we also can't have plus or minus a half. Now let's talk about the range. So a value of function gx is in the range of the composite function only if x is in the domain. Well, what I like to do for this one is actually work out what the composite function is. So if I substitute gx into function x, I end up with 2 on 4x squared minus 1. The range of that, if that was just a function by itself, its range would end up being less than or equal to -2 or greater than 0. But Remember, we said x can't equal 0. So even though we could substitute 0 into this composite function, x is not in the domain. Because you see, we're not actually substituting into that new function. We're substituting into gx first and then getting that and substitute. So if I can't substitute in the gx, I can't get the end result out for function x. So because we know x isn't in the domain, whatever that result is, we have to pull out of the range. So we can't get -2. So other than that, we're fine. So all it does for our particular one is instead of the range being less than or equal to -2, we're saying, well, actually, for the composite function, we can't get -2. So the range would be less than -2 and greater than 0. Let's go back the other way then. Let's do subfunction x into g of x. So x must be in the domain. So this time we know x can't equal 4. But function x must be in the domain of g of x. So this time we're substituting f into g. But we know we can't substitute in x equals 0. Therefore, 2x on 4 minus x can't equal 0. Well, that means x can't equal 0. So our domain for this one, all real x except 0 and 4. So the range of the composite, here we go. Let's work out the composite function. As I just find it easier to do it this way. 4 minus x all squared over 4x squared. So if that was just the function alone, again by drawing it, we could work out that it's always greater than or equal to 0. That one's a bit easier because look, everything's squared. So we know the range of that has to be greater than or equal to 0. But x can't equal 4, remember. Right? It's not in the domain. So if I was to substitute 4 into this new function, whatever answer we get, we can't get, if you get what I mean. Because I'm not allowed to sub 4 into it. And that also, by coincidence, turns out to be 0. So our range, instead of just being greater than or equal to 0, which it would have been, will now just be greater than 0. There's this one other type of function we need to know about. Remember the empty set in sets? Yeah. So if the domain should for some reason turn out to be the empty set, we've ended up excluding every possible one, then the function is known as the empty function. All right. 4e, we'll have a play with that.